Welcome back to video lecture, students. Today's topic is Qpsk from Unit 4 Digital Modulation Scheme. The course outcome of Unit 4 is analyze the spectral characteristics and bit error rate performance of digital modulation techniques. So in the previous classes we discussed about two different modulation schemes. One is BFSK and another one is BPSK. So this is Qpsk. Qpsk means quaternary phase shift gain or quadrature phase shift gain. From the name itself, we can say or we can define four phase shift are going to be introduced in this technique. So according to the definition, phase shift gain means we are going to modulate the high frequency carrier's phase. So the difference between PSK and Qpsk is in BPSK only two bits are going to be considered, that is 0 and 1, whereas here in quadrature phase shift gain two symbols are transmitted at a time. So we can able to produce 2 power n combinations at a time, that is 2 power n is equal to 2, that is number of symbols are 2, so we can produce 4 combinations 0 0 0 1 1 0 and 1 1. So that is why it is called as quaternary phase shift gain or quadrature phase shift gain. So combining bits will reduce the signaling rate as well as the carrier frequency. Transmission channel bandwidth also reduced. So these are all key points you have to remember for Qpsk. So this is a general table to represent Qpsk when you combine two successive bits. So for our convenient, we are taking the symbols from 1 to 4. Let us assume I is equal to 1. For I is equal to 1, the input successive bits are going to be 1 0. So the symbol is represented as S1. The corresponding phase shift in the carrier is pi by 4, that is 45 degree. Similarly for 2 it is 0 0, symbol is S2, and 3 pi by 4. Similarly 3 0 1 S3 and 5 pi by 4. I is equal to 4 1 1, symbol is 4 7 pi by 4, that is 45 degree, 135 degree, 225 degree, 315 degree respectively. So according to the requirement we can choose either a quaternary phase shift gain or BPSK. So here also two levels are introduced. There is no change in the amplitude. So 1 means plus 1 volt. If the bit is 0 means minus 1 volt. So Qpsk transmitter. It is otherwise called as offset Qpsk or OQPSK. In other words, it is called a staggered Qpsk transmitter. So why it is called as offset means when there is a modulated signal, the bipolar NRZ encoder produces bit stream, so which is given to demultiplexer. This demultiplexer divides the bit stream into even and odd signals. See, even bits are generated after odd bits generation, so it takes one period of delay, so that delay is called as offset delay. Okay, so this is general block diagram. The working principle is same. So binary data is given to bipolar NRZ encoder. Here one demux is introduced for separating even and odd bits. Balanced modulator, this is for carrier recovery, and one adder is there. It is similar to PSK, whereas for 4 phase shifts we are introducing one additional block demux in this block diagram. So the binary data is given to binary bipolar NRZ encoder. So bit streams are converted into bipolar non-return to 0 levels. So that is given to demultiplexer. Demultiplexer is used to divide or separate even and odd bit streams. So the bit derivation of symbol is 2TB, as carry symbol contains 2 bits. So the operation of balanced modulator is here the high frequency carrier is going to be multiplied with either even bit stream, or here it is odd bit stream. So in carrier also there is 90-degree phase shift is introduced. Here also one phase shift, here also one phase shift. So this is considered as even bit stream, this is as odd bit stream. So the combination of SE of t and S naught of t produce Qpsk signal. So this is the operation of this circuit. So SE of t is equal to B of t into root p sin 2 pi f naught t. S naught of t is equal to B naught root p cos 2 pi f naught of t. So combine these two, this will produce our final signal. The same thing can be generated without offset. So to reduce this offset null, the even bit streams are delayed by 1 bit period TB. Then both even as well as odd bits will be starting at the same time period. In that way we can reduce the offset null. So there won't be no offset when we delay the even signal. So this is the signal representation as I told earlier, 45 degree, then 135 degree, then our next phase should be occur in 225, then 315 degree. So according to the symbol duration 0, 1, 0, 0, 1, 0 and 1, 1 case. The corresponding signal levels are represented here according to this equation. So this is a Qpsk receiver. Qpsk signal is given to correlator, and we have one multiplexer. So the difference between PSK and here is the introduction of multiplexer at the final stage. So the Qpsk signal is given to correlator 1, or upper correlator. Similarly, it is given to the lower correlator. The combination of product multiplier and integrator is called as correlator. So the Qpsk signals given to upper correlators to obtaining the even bit stream. Here it is to reproduce the odd bit streams. In the multiplexer operation is, it is going to combine these two, and automatically odd and even signals present are neglected, and we can able to produce n number of bit streams based upon the outcome of these two. Upper integrator equation is given here, and when you simplify this equation, this leads to B of t root ps into TB as we discussed earlier. Then correlator output is given, and there is an ambiguity in Qpsk output, that is it won't provide to determine whether the transmitted signal is a positive or negative signal. So that is a major drawback, and this is the signal representation of Qpsk signal. In the previous case we will consider 2 pi f naught of t plus theta r omega r pi. Here we will introducing 2n plus 1 or 2n minus 1 pi by 4, that is 45 degree, 135, 225 and 350 degree phase shifts are introduced based upon the symbols. So this is the general equation for this Qpsk signal, and this is the Euclidean distance diagram to represent Qpsk, and the distance is calculated as d is equal to 2 into root EB. When we compare this with BPSK, that is root EB, here it is 2 into EB. Power spectral density can also be obtained by using the above equation, and the bandwidth requirement of this Qpsk is 2 into 1 divided by 2 TB, so this is equivalent to FB. So when we compare with that Qpsk and BPSK and BFSK, BFSK need 4 times of FB, whereas Qpsk binary phase shift keying requires 2 FB, whereas Qpsk requires FB alone. So the bandwidth is reduced when we improve the symbol rate. Advantages of Qpsk: bandwidth is less compared to BPSK and other modulation techniques. Information transmission rate is high and power remains stable. This is the error probability of Qpsk signal. So from this we can conclude that the error function of Qpsk signal is equivalent to ERFC root of 2 ES divided by 2 N naught. Thank you.